Hello everybody, welcome to our lesson. Today's topic is Lenz's law. This is the goal of the lesson. At the end of the lesson you'll be able to explain the physical results of Lenz's law. You already know that if the north end of a magnet moves towards a coil, the current is anti-clockwise. If it moves out of a coil, the direction of a current is clockwise. And we know it because we have observed it from Faraday's experiment. But we still don't know the explanation of this observation. And in this lesson, we will try to understand how the induced current set up its direction. So, right over here we have a circular loop of conductor. Let's say it's a wire and it's stationary. And if we move a bar magnet towards a ring, the magnetic flux through this ring will increase. And you know from Faraday's law that increase in the magnetic flux would cause an induced EMF, hence induced current. So the interesting question is, what direction is that current actually going to go in and why? We have two options. The current could go in the clockwise direction, that's given by the number 1. Or it could go in the counterclockwise direction, that's given by the number 2. So which of these two do you think the current will actually go with and why? And let's discuss each direction one by one. We know that current flowing through a wire actually on its own will induce a magnetic field. So let's think about the type of magnetic field that this current would actually induce. If it's going in the clockwise direction, remember we use the first right hand rule. I can take my right hand, curl my fingers in the direction of the current, and my thumb will show the direction of the magnetic field. And this is the magnetic field induced from the first scenario. And with the same rule, I can find the direction of the magnetic field in the second scenario. Note that they have opposite fields because they have opposite current. So let's start with the first scenario. Here we have the loop of wire and we move the magnet towards the loop, and increase in the magnetic flux causes to induce current in the clockwise direction. And induced current creates an induced magnetic field, which I'll show here with orange. The direction of the magnetic field we have found by our right hand. It would be additive. Notice that it would be additive to the existing magnetic field from the bar magnet. So you see that the magnetic field of the bar magnet is to the right, and magnetic field, the induced magnetic field of a loop is also to the right. So in fact it would increase the magnetic flux even more. In fact, in this region the magnetic field would increase even more. We have an increased flux here. Well, what would that do? If the flux increases even more, the current is going to increase. The current is going to increase even more, which is going to make the magnetic flux increase even more, and which makes the current increase even more. And you would have this never-ending cycle where the current keeps increasing, the flux keeps increasing, and you would have this energy that's appearing out of nowhere, which would violate the law of conservation of energy. And so that's a pretty good argument for why we would not expect the clockwise scenario. We would not the current that has been induced to induce a magnetic field that goes in the same direction as our increase in flux. So just by deducting reasoning, we know that this is going to be the scenario, and let's see if we think about what happens here. We can do the right hand rule again. Well, now this would induce a magnetic field that would decrease the magnetic flux. So it would produce a magnetic field. The current right over here would produce a magnetic field that's going to the left, and the magnetic field from a bar magnet is toward to the right. And so the induced magnetic field from the induced current will go against the change in magnetic flux. And this makes sense because we won't go into this never-ending positive feedback loop where the current keeps getting strong and stronger and the magnetic flux keeps increasing and increasing and increasing. And we see here the fields are opposite. And this idea that the orientation of the current that is induced will produce a magnetic field that counteracts the change in magnetic flux, this is the Lenz's law. So Lenz's law states that the magnetic field, induced magnetic field, always opposes to the changing magnetic flux. It will always oppose to the magnetic field. And it was formulated by Heinrich Lenz in 1833. While Faraday's law tells us the magnitude of the EMF produced, Lenz's law tells us the direction that current will flow. It's a qualitative law that specifies the direction of induced current, but states nothing about its magnitude. Lenz's law is typically incorporated into Faraday's law with a minus sign. And the inclusion of which allows the same coordinate system to be used for both the flux and EMF. The result is sometimes called the Faraday-Lenz law. And Lenz's law states that the direction is always such that it will oppose the change in flux which produced it. This means that any magnetic field produced by an induced current will be in the opposite direction to the change in the original field. Now, one more time, let's go back and do Faraday's experiment. This is the last time, I promise. But in this case, we won't move the magnet back and forth of a magnet. Instead, we will just drop a magnet from above the coil. The reading of a voltmeter is plotted into a graph. EMF against position of a bar magnet. And observations are as follows. Magnet is at rest or near the coil. You see from the graph, no voltage observed. Magnet is moving toward the coil. Some voltage measured, rising to a peak as the magnet nears the center of the coil. And third, magnet passes through the middle of the coil. We see it from the graph. Here, measured voltage rapidly changes sign from minus to plus. And magnet passes away from the coil. Voltage measured in the opposite direction to the earlier case of the magnet moving into the coil. These observations are consistent with Faraday's law. Although the stationary magnet might produce a large magnetic field, no EMF can be induced because the flux through the coil is not changing. When the magnet moves closer to the coil, the flux rapidly increases until the magnet is inside the coil. As it passes through the coil, magnetic flux through the coil begins to decrease. So you see the interesting thing. The magnetic flux increases, but EMF decreases. And the most important observation here is when the magnetic flux increases, the induced EMF decreased, and when the magnetic flux is decreased, the EMF is increased. And that's why we put the minus sign in Faraday's law. So minus sign tells us that the increase in flux will decrease EMF, decrease in flux will increase EMF. It simply says that any change in the magnetic flux opposes and induced EMF. So this is the Lenz's law. Well, this is the end of our lesson. If you like it, please subscribe and share. Thank you.